Our next speaker is Jonguk, and he speaks on renormalizability and non-uniform partial hyperbolicity.
Thank you very much. It's a pleasure to be here. I'd like to thank the organizers for giving me this opportunity. First thing is I'm not 100% confident that these microphones are picking up my voice. So if you want me to speak louder, please tell me. If you want me to write bigger, also tell me. And if you have any questions, please don't hesitate. So I want to talk about critical points, and I'll start in one-dimensional case because in one dimension, critical points are trivial to identify. So in 1D, let's take a map. So definition. Let's say you have a map defined on some one-dimensional phase space. I'll just call it X into itself. And this one-dimensional space, I mean, common examples would be an interval on the real line, or maybe a circle, or it could be something complex, like a domain in the complex plane, or the Riemann sphere, and so on. But for any such one-dimensional map, we say that a point C naught in this space is a critical point if the derivative of the function is equal to 0 at this point. We further qualify such a point to be non-flat. C naught is non-flat if, well, the first derivative is equal to 0, but some higher order derivative is not equal to 0. If there exists some n such that the nth derivative of f at this point is not equal. And the smallest n, so that this holds, is called the degree of the critical point or the order of the critical point. And the term non-flat comes from the following geometric consideration. So if you were to draw the graph on this map, right? And let's say it has a critical point at the origin, then the fact that the derivative is equal to 0 means that the graph of this function should be tangent to the horizontal line, right? But if it's non-flat, then it can't be completely flat at the critical point, because it's got to be at least less flat than the graph of some power map. Non-flat. Okay, so this is what a critical point is. As you can see, the definition is very simple, but these critical points play a very crucial role in one-dimensional dynamics as a source of nonlinearity. So it's what allows very simple maps, like the ones that I'll give in just a second, to have incredibly rich and complicated dynamical behavior. The simplest setting in which one can try and study the dynamical effect of a critical point is within the class of unimodal map, which Daniel actually mentioned in his talk. It's a definition. So this is kind of the simplest dynamical system that has a critical point. So we say that a map defined on an interval to itself is unimodal if it has exactly one critical point of the lowest order, namely order 2. So if there exists a unique critical point, C naught, let's say quadratic type, meaning second derivative at this point is not. This is what a unimodal map is. And a standard archetypical family of unimodal maps is, of course, given by the family of quadratic polynomials. So, for example, the quadratic family gives us a one-parameter family of unimodal maps if you were to parameterize it in the following way. So let's say that the quadratic family consists of all maps of the form f sub a equal to x squared plus a, where a is any real number. This is the real number. So the dynamics of this family is now completely understood. And the interval in this case, well, it's just any interval on the real. Oh, but for this family, you mean? Okay, so for this family, I guess the interval is not always well defined. So if you have the parameter space for this family, which we'll identify with the real line, the value is A, the interval, it only strictly satisfies the definition if you only look at the parameter values between -2 and 1. In this case, you can show that this has a fixed point, and then you take negative of that fixed point, and this interval in between is invariant. So yeah, so we consider this whole family, but actually the interesting stuff happens in this interval. And it was very difficult to actually figure out everything that goes on there. It took many mathematicians, including several Fields medalists, more than 1 decade to figure out what happened. Yeah. But the main tool that they used is something called renormalization theory of the unimodal interval maps, which is what I'm going to, the main thing that I'm going to talk about, but in a higher dimension. Okay. All right, so this is very simple version of the story in 1D. I would like to now go into 2D unless there are any questions. By the way, just for fun, so this is the real quadratic family, but you can of course think about the complex quadratic family as well. In which case we have a complexified version of this interval between -2 and 1/4. Does anyone know what that set is? The complex version of this interval? The Mandelbrot extends to this very complicated fractal, which everyone here must have seen, right? So yes, so I think it's sometimes hard to convince people that interesting happened on this interval, but then once you see the complex version, it's very interesting how difficult it is. Okay, now let's go into 2D. In 2D, the analog of the quadratic family is given by the Hénon family, which I will parameterize in the following, right? So this is the family H of maps of the form, let's say capital F, and it's parameterized by 2 real values, A and B. And it's maps of the form. So the first coordinate will be x squared plus A minus BY. And the second coordinate will just be x. Okay. So the quadratic family with 1 parameter, so you can visualize it by the real line. This is 2 parameter family, so I like to visualize it by the parameter plane. Then by the family of Hénon maps with the plane. And let's say the horizontal axis is the A axis, and the vertical axis is the B axis. A simple computation shows that the Jacobian of this map is identically equal to B, right? So the second parameter actually tells you exactly what the Jacobian is. So if you're in the upper half plane, you have orientation preserving Hénon maps, orientation reversing Hénon maps. If you look at the line B is equal to 1, those are all the area preserving Hénon maps, area expanding Hénon maps, and these are the area contracting or dissipative Hénon, right? Let's look at the line when B is equal to 0. Well, there you have the degenerate Hénon maps, which you can actually identify with the quadratic polynomial, right? And it's very simple to see, because when B is equal to 0, the dynamics that comes from iterating this map, in which case you can just ignore the second coordinates, right? And then just, so this A axis, you can identify with the quadratic family, which shows you that the Hénon family is a 2-dimensional extension of the family of quadratic polynomials. Okay? So the Hénon family is, I would say, one of the best studied examples of 2-dimensional system. And although there have been many remarkable results about this family, I would say overall, its dynamics is still wide open. It's still quite mysterious. So the goal, my goal and my co-authors, our goal was to try and take what worked for the quadratic family, which is the renormalization theory of unimodal maps, and try to find a higher dimensional generalization so that it can be applied to the study of non-degenerate phenomena. And actually a key difficulty was to try and identify what unimodal could mean in this higher dimensional context. What is a critical point for a surface diffeomorphism? Because obviously we can't define it in the same way as in 1D, because, well, as I said, the Jacobian is never equal to 0. Right? So you can't say, oh, the critical point is where the derivative is equal to 0, and then try to find where that is. So actually, I think most of the talk will be just in identifying what this notion should be. And actually, we didn't expect this, but the right notion of unimodality, the right notion of a critical orbit, turns out to be exactly the failure of uniform hyperbolicity, or actually, in this case, uniform partial hyperbolicity in the system. Okay, so this is why I kind of thought that it fits with the theme of the talk. Okay. Okay, I think those are all the motivational preliminary discussion. Any questions before I start with the theory? No? Okay, we'll come back to this picture at the end. Okay. All right, so let's try to develop this higher dimensional renormalization theory. So let's take our map. So we will say our phase space is omega is a Jordan domain. And R2. So by Jordan domain, I mean a domain looks something like this. Yeah. So it's a topological disk whose boundary is a topological circle. And then we will take the map F, which maps omega compactly into itself. And we will make some regularity assumptions about F. So we'll assume that F is C2, diffeomorphism. We'll assume orientation preserving, and we'll also assume that it is specific. So the Jacobian is everywhere bounded away from 1. Yeah? Actually, for the theory, we need something stronger than dissipation. We actually need something which I call proper dissipation. But it's not really going to come up, so let me just kind of sweep this under the rug. But I will just say that a Hénon map is known to be properly dissipative if the Jacobian is less than 1/4. Okay? So it's not something which is very hard to satisfy, at least within the Hénon. Okay, so this is the setup. So you have this Jordan domain, and you have this map F, which maps it compactly into itself. Like so. And we will say that such a map is renormalizable if the following condition holds. And I'll first give kind of an intuitive philosophical definition, and then I'll give the more concrete, rigorous definition right after. So philosophically speaking, generally speaking, you would say that a dynamical system is renormalizable if it exhibits some kind of self-similarity at a smaller scale. Okay. In this particular instance, we would say that definition F is renormalizable if there exists a periodic subdomain in the phase. If there exists an R periodic for some R bigger or equal to 2, Jordan subdomain. Let me call it D. Compactly omega. So what do I mean by a periodic subdomain? Let me use different color. We'll try to use blue. So if we have a Jordan subdisk inside this domain, then we would say that it's periodic if, when you map it, it takes it off of its original spot. So its image is disjoint from itself, right? And then you keep iterating, all the intermediate images are disjoint, but then once you map it by the period R, it goes compactly into the original. So you map it once, it goes somewhere else, because the period is strictly larger than 1, but then you keep mapping, and eventually, once you do it R times, it will go compactly into. And we can define the return mapping onto this smaller domain by just iterating F by the period. Yeah. So this is called the first return map. Which is, okay, I'm going to denote by little p curly r of F, which is equal to F compose R times restricted. So this actually is consistent with the general definition that I gave before, right? Because we started with a dynamical system, which takes a disk compactly into itself. And when it's renormalizable, you can see that there's a little copy of this disk. And under the dynamics, it is mapped compactly into itself. So there's a little mini version of the map at a smaller scale. So this is what it means to be renormalizable. Any questions so far? No. So that's one big difference between renormalization in higher dimensions versus one dimension. Because in one dimension, your domains are interval, whose geometries are very simple. But here, the geometry could be off. The only thing we assume is that the topology is. Any other questions? Sorry? Oh, why is it? Okay, so this first return map is also sometimes known as pre-renormalization. So that's why there's a little. Okay. And why is it called pre-renormalization? Well, because it precedes renormalization. Which is defined to be this map, but if you were to just take the first return map, it's defined on something strictly smaller than the original domain. So what you want to do is rescale, renormalize the scale of the map, right? So you zoom in so that you enlarge the little domain, and then you have a map of the same scale as the original, right? So we call that renormalization. We call this R of F, and this is equal to, let's say, rescaling little p. Okay. No. So I'm going to be vague about how you want to rescale. In fact, I'm not really going to talk about it so much, but no, you need to be careful with how you rescale. So the only thing I'm asking is that it maps the domain compactly into itself. But of course, yeah, actually for now, that's all we're asking. That's all we're asking. All right, good. So we have once renormalizability, and we would say that this map is twice renormalizable if the renormalization of F is also renormalized, right? So if there is another domain, let's say a little disk here, so that if you map it by the return map, it goes somewhere else. So if you map it again, it goes compactly. Then it's twice renormalizable. So you can define the second first return map, and then you can keep doing this iterating this procedure, right? So in this talk, we will assume, where should I go? Okay. In this talk, we'll assume that our map is infinitely renormalized. Assume F is infinitely renormalizable. So what does this mean? It means that, well, you can renormalize infinitely many times. So there has to exist for all n, there exists an Rn periodic Jordan subdomain. Let me call it Dn, and they have to be nested. So Dn will be compactly contained in the previous renormalization domain, like so. And in this case, you can form a topological attractor for the system by taking a nested intersection of all these cycles of periodic domain. And we call this topological attractor the renormalization limit set, or something more simple, the odometer. The odometer of the system is defined, let me call it capital lambda. And you take all the cycles of level n. So you take the nth renormalization domain, which is Rn periodic. So you take all of its images take the union, and then you take the nested intersection and go to 1, 2. Okay. All right. So as I said, if it's infinitely normalizable, then we have all these first return maps, right? So let's say that the nth first return map is given by PRN of F, which is equal to F iterated by the period of the nth domain, which is Rn, restricted to Dn, like so. And then after rescaling, we obtain the nth renormalization, which is Rn. So we obtain the sequence of dynamical systems, which are all of the form, it takes a Jordan domain and it maps it compactly into. And it makes sense, it's natural to ask, well, what happens as you take higher and higher renormalization? A more kind of intuitive way to ask that same question is, what happens if you take this dynamic and you zoom in deeper and deeper? What does the dynamic start to look like? There was a question? Okay, 2 questions, yes? Rn must be increasing because these disks are nested. And the relative period must be at least 2. Yeah, exactly. That's right. Back there, yeah. Rescaling, okay. So in 1D, it suffices to just take an affine rescaling. In this case, that won't be actually a good way to rescale. So rescaling is kind of the right definition for rescaling. There isn't a unique definition. Typically, you want something practical, right? So in this case, there's a certain specific rescaling. It's nonlinear. It's kind of technical to define, which will make this work, but I'm just kind of not getting into it. So it's not going to be affine. Any other questions? Yes? Good question. A priori, we don't know. A priori, we don't know. Yeah. So it's not obvious at all. In fact, a priori, we don't know if it traps most of it. It traps some. There could be other things, right? Any other questions? Okay. All right. So we want to know what happens as you keep renormalizing, as you keep zooming in, what does the dynamic look like? And one very simple but very important observation that you can make right away is that the renormalizations will tend to look more and more one-dimensional as you renormalize. Okay, so let me just make that note. Note that Rn of F will become more and more one-dimensional. Yes. Okay. And I will give you a very wishy-washy, vague answer. Okay? And so you can kind of think that the distance of a two-dimensional system to a one-dimensional system is given by its Jacobian, right? But if you're renormalizing, you're essentially taking your map and composing it to itself a bunch of times. So if it's dissipative, it's area contracting, then as you iterate more and more, the area will degenerate to you, right? So if there's any kind of meaningful limit, it should be to a one-dimensional system. So that's kind of a basic observation. But to say anything more, what you need to do is to try and analyze the geometry of the Hénon. Okay, so this turns out to be the most important. So let me actually draw this thing. So this is obtained by taking all these cycles of domains and taking the nested intersections, so you'll get some kind of set, which, as I said, may not be minimal. It's kind of designed to look like a Cantor set, but you don't know a priori that it's a Cantor. Because in order for it to be a Cantor set, you would need to make sure that all the connected components are singleton, but that we don't know, right? So what could happen is maybe some of these domains, as you go deeper and deeper, doesn't shrink, right? In order to guarantee that it shrinks, you have to know something about the geometry as you zoom in. Okay, so this is what we need to try and control, what we need to try and understand. Okay, so how do we do this? Let's make some non-trivial observations, which requires proofs, but for now, we'll just take it as facts. So if you look at this totally invariant set, lambda, something you can prove, which is not obvious, is that it has to be uniquely ergodic. Lambda is uniquely ergodic. Uniquely ergodic. So it has a unique invariant probability measure, which I'll denote by mu. Okay. And with respect to this probability measure, it has two Lyapunov exponents on the odometer. Lyapunov exponents. Exponents are, there's two of them. One of them has to be 0. So one of them 0, and the other one has to be negative since it's contracted, right? So this negative number, let me call it log lambda. Okay. So this is not obvious, the fact that it's uniquely ergodic, the fact that one of them has to be 0, but it's something that you can. Okay. So I hope that it's okay to assume that everyone here is kind of comfortable with the Lyapunov exponent, right? So if these two are the Lyapunov exponents, it means that for a typical point, it has a stable direction and a center direction, right? And a stable manifold and a center. Yes. It's general. When you have an infinite renormalizable surface diffeomorphism, then this holds. Well, you have to assume proper dissipation. Okay, so it has to be dissipating kind of strong. Any other questions? Yes, it's fine. No. So you have to assume the two conditions: infinite renormalizability and proper dissipation. They're independent. Yeah. Okay, so these are the Lyapunov exponents. Okay, so if you take a typical point here, then it has a stable manifold, which I'm going to call WS, and it has a center manifold corresponding to Lyapunov exponent 0, which I'm going to call, okay, let me draw it with blue, which I'm going to denote by W's. Okay, and if we're going to try and understand the geometry of the system, what we're going to do is we're going to apply Pesin theory. So what does Pesin theory tell us? It gives us the following statement. So Pesin theory tells us that fix any small epsilon, right? Okay, question, yeah. Oh, that's a good question. I think C1 plus alpha is enough. C1 plus alpha. Any other questions? No. All right. So Pesin theory applied to this setting tells us that you can pick any really tiny small number, epsilon. Then for almost every point, P naught in the odometer, there exists some constant, let me call it capital L, which depends on the epsilon and the point, such that, okay, I'm going to say a term. It's not going to make sense, but then I'll explain what it means. Such that P naught is L epsilon Pesin regular. Okay, so what does this mean? Let me explain by drawing a picture. Okay, so if you take a typical point like P naught, which is this L epsilon Pesin regular, then we have the following picture for the local dynamics of F near the orbit of P naught. So let's draw the orbit of P naught. So let's say this is P naught, P1, P2, so on. Forward orbits, backward orbit, P minus 1, P minus 2, and so on, like this. And let's say it's L Pesin regular. So it has this direct stable direction and center direction corresponding to Lyapunov exponents log lambda and 0 respectively. So let me call the stable direction E sub S and the center direction EC. Okay, so we have these two directions, and then you can push them forward and push them back by the dynamics. So we can move these around. Let's draw them like this, and maybe this looks something like that. Okay. So this is the local picture, and to go from one point to another, one orbit point to another, you have to apply this nonlinear dynamical system F. Okay. Well, the fact that this point is L epsilon Pesin regular tells us that the local dynamics of F along this orbit can be linearized in what I'll call epsilon shrinking 1 over L neighborhood of the orbit of Hénon. Okay, so what does that mean? So what it means is you first start off. So what you'll do is you'll cover this orbit by balls whose radius is shrinking exponentially. Okay, so the initial ball will have radius 1 over L because it's L Pesin regular. Yeah. And then as you go forward in time, you will shrink the diameter of this ball by some slow exponential factor as you go further and further. Yeah. So what do I mean by slow exponential factor? I mean, well, along the stable direction, you have contraction by lambda, right? Because the input of exponent is log lambda. So by slow exponential, I mean something slow compared to that rate. So something slower than lambda would be lambda to the epsilon, right? So this is how we shrink these balls. So this will be the same diameter as before, 1 over L, but I shrink it by a factor of lambda to the epsilon. So it's some number smaller than 1, but it's much bigger than the taking, right? So if you go twice, then it will be 1 over L, but you shrink twice by a factor of lambda to the epsilon, and so on and so forth. Okay, so this will be 1 over lambda, 3 epsilon. So this is how you cover the forward orbit. The backward orbit is similar, except now you're going backwards. So this will be 1 over L lambda epsilon, 1 over L lambda 2 epsilon. And so okay, so this, yes. Yes. Yeah, so that was the second statement that I was going to make, is that the angle between the transverse direction will be 1 over. If you the local setup, yes. Yeah, it's allowed to go shrink by a factor of lambda. But then we can say a little bit more, that we can actually find changes of coordinates on these neighborhoods, which turns F, which is some nonlinear map, into something which is very simple. Okay, so there are changes of coordinates on these neighborhoods. Let me call these neighborhoods, okay, I'm kind of overpacking this blackboard, but okay, I have no choice. Let me call these neighborhoods UI. So at P naught, it's U0, U1, U2. This is U minus 1, U minus 2, and so on. Okay, so on each of these U's, there is a change of coordinates, Pi, such that these neighborhoods are transformed into, well, downstairs, you again have this exponentially shrinking ball. But the picture looks a lot simpler. For one, the stable and center direction, they're sent to exactly the vertical and exactly the horizontal direction for each of these points. Like so. And the map, which takes you from one orbit point to another, if you conjugate it by this change of coordinates, becomes the most simple thing that you could imagine, which is just a linear map, which you can pretend is just 1, 0, 0 length. So instead of some unknown transformation from this ball into this one, or at least partially overlapping this one, you'll actually just map it by doing nothing along the horizontal and contracting the vertical by a factor. So you have this at each of these neighborhoods. Okay. So this is what I mean by linearizing the dynamics of F along this way. Questions about this? This is kind of an important thing. Yeah. So you can do it for almost every point, but just you might have to contract the initial ball in order to make it. Okay, so what does this tell us about the geometry of the stable and center manifolds, which was what we were at, right? So in fact, there's a very simple description once you set this up, because downstairs, the stable manifold is what? Down. What is a one-dimensional curve that is being contracted by lambda? Is going to be the vertical axis, yeah? So downstairs, the stable manifold is just given by the y-axis, like so. Then the local stable manifold upstairs, the actual stable manifold is just given by you take the pullback under the chain. Okay, so this gives you little pieces. Stable manifold. And something I didn't say, but something you can prove is that you control the CR norm of these changes of coordinates, which in turn lets you control these pieces of the stable manifold. Okay? Once you have the same thing with the center manifold. Downstairs, the center manifold is just the horizontal axis. And then you can lift that to the actual center manifold by the changes of coordinates. Okay. So this is what Pesin theory gives you in this set. Questions? Okay. So let me remark that actually this picture is two pictures put into one. Yeah. Because, well, we drew this picture in order to control the stable manifold and the center manifold. But these two manifolds are obtained from different sides of this picture. So for example, if you just want the stable manifold, then you don't actually care about what happens in backward integration. You only care about what happens in forward integration, right? Because what is a stable manifold? It's a set of all points that share the same future as your actual point P0, right? So you only care about what's happening forward in time. Yeah. So if you just want to be able to control the stable manifold, then you only need this side of the picture. And if you have just this side of the picture, then we would say that this is not Pesin regular, but that it is L forward regular. Okay, so if you just have this half. And if you have just this half of the picture, then actually this is enough to allow you to control the geometry of the center manifold. In which case we would call that L backward regular. Okay. Yes. Sorry? Oh, no. You don't have unique center. So it's a sum invariant curve. Yes. No, it's not unique. So you just need something as kind of a reference. But the only unique canonical thing about the center direction is the jet of this curve. So at the point, its derivatives will be unique. But how you extend it to something local is not. Yes. Yeah. That's right. Yeah. That's right. Yeah. Which is what Pesin theory gives. But I'm not going to get into it. All right. So I just explained how you could just have a half of this kind of picture. So there's forward regularity for controlling stable and backward regularity for controlling center. So let me denote the set of L, okay, forward, backward, and Pesin regular points in the odometer by lambda L. And the forward regular points will be denoted by superscript plus, backward regular will be superscript minus, and Pesin regular will be superscript P. Okay. And it's not hard to observe that your system F is uniformly partially hyperbolic, if and only if every point is L Pesin regular for some uniform. So if and only if there exists some uniform constant L such that the odometer is actually entirely L Pesin. This is uniform partial. Okay. So when your system is uniformly partially hyperbolic, life is actually much simpler, right? And to demonstrate, let me draw a little cartoon to kind of argue why it should be easier. Yes, Keith? Okay. So I should put little epsilon. But epsilon is just constantly fixed, so I kind of wanted to forget. So technically, I should. Okay, so suppose that it was suppose that we had uniform partial hyperbolicity. Okay, then the picture simplifies in the following way. Okay, so let's pretend that we have the following very simple situation. So let's say our domain looks something like this. Okay, and we have this odometer here. And let's say that this, as I drew it, this domain is very thin in the stable direction. So let's say that the stable manifolds of these points are pointing upward, and the height of this domain is something much less than one of them. Okay, let's say you have this set, just for me to prove a point. Okay, so if it's uniformly partially hyperbolic, then all these points, every single point, has stable manifold, which is at least as long as the height of this domain. Right? So if you have this configuration, actually, you're not really dealing with a two-dimensional system anymore, because you can just factor in the stable direction, and then you're just reduced to one dimension. Okay, so there's nothing kind of interesting taking place due to the fact that you're in higher dimension. Okay, so this would be a very nice, easy case. Unfortunately, if your system is infinitely normalizable, it cannot possibly be uniformly partially hyperbolic. So it's something that you can prove. Okay. So by our assumption, our system looks like this. It has this odometer, and it cannot be uniformly partially hyperbolic. And here's where we define this notion of unimodality. We would say that a system, a non-uniformly partially hyperbolic system, is unimodal if the cause of the non-uniform partial hyperbolicity is due to the existence of some critical orbit, which I'll define right now. Let's go to this board. Okay. Finally, we define what a critical point is. We'll say it in definition. So let's say we have an orbit in the odometer. Then we will say that this is a critical orbit, a regular critical orbit of quadratic type. A regular critical orbit of quadratic type. If the following conditions are satisfied. If the following. So we require the following. So the simplest way to define a critical orbit is to just define it like this. So an orbit is a critical orbit if it has well-defined stable manifold and it has well-defined center manifold. And if these two manifolds are transverse, then we would just have Pesin regularity, right? So we would assume that they're not transverse, meaning that they have to be thin. Okay, so this is the simplest definition of a critical orbit, but let me specify some extra conditions just to make our discussion simpler. So we assume that it has a well-defined stable manifold, so we have to have forward regularity, right? So we'll assume that the critical value has nice stable manifolds. So we'll assume that the critical value is, well, we could just assume some forward regularity. So I could just put L here, but for sake of simplicity, let's put 1. So let's say C1 is 1 regular. 2, we want center manifold. So let's say that the critical point is one of the backward regular points. Yeah, like this. Okay. So then the setup looks something like this. You have the critical value, 2, 3, and so on. And we have the critical point, C naught, C minus 1, C minus 2, and so on. So the critical value is forward regular. So we have this picture up there, but just going in the forward direction, right? So we have this neighborhood of initial size, some uniform size, but as you go forward, it will shrink exponentially slow. And it has this nice vertical stable manifold, which comes from linearizing this local dynamics by, let's call P1, P2, so on. Neighborhoods. Okay, so the orbit points are sent to the origin. The stable direction is sent to the vertical direction. And the transition from one orbit point to another is like 1, 0, 0 length. Okay, so this is the picture that we have if you start from the critical value and you go forward. We have this nice contraction in the vertical direction. And we have a similar symmetric picture as you go back from the critical point, like this. So you can straighten these charts. So, and downstairs, the map is just this simple linear map, 0, 0 lambda, and the center direction is sent to the horizontal direction, and the the center manifold is just the horizontal axis. Okay, so this is the picture that we have, assuming condition 1 and condition 2, and then condition 3 will assume that when you take this center manifold and you map it forward, you will assume that it's not transverse, because in that case, this will just be a regular Pesin regular orbit. You'll assume that this, when you map it to here, has a tangency. And since we're assuming that this is quadratic type, we'll assume that the tangency is of order 2. Okay? So when we map this center manifold at the critical point to here, the picture will look something with the quadratic tangency. So that's the third condition. I don't know if I have enough space. Right here, the image of the center manifold and the stable manifold of the critical value has quad 10. All right, so very good. So then the last thing I want to point out from this picture is that, so if you have a regular critical orbit, then you can actually uniformize its local dynamic in a similar spirit as in the Pesin regular case. So you want to try and make it as standard and simple as possible. But you'll notice that to go from here to there, you can't just try to make it look like this linear map, right? Because if you apply this linear map, then the horizontal will just go to horizontal, which is not the picture that we have, right? What we actually have is if we take the horizontal and we map it across, then the picture should actually be a parabola, sideways parabola. Okay, so the way we're going to uniformize the transition at the critical moment is by using a Hénon. So if you were to map this chart to this chart by x squared minus lambda y and x, then it will take this horizontal line and it will map it to it. Okay, so this is a regular critical orbit, and it is controlled in this local way by this kind of uniformity. Any questions about it? You have critical orbits. Up to the critical moment, it's linearized just like in the Pesin regular case. After the critical moment, again, same, but the transition is now something nonlinear, which turns the center manifold into a sideways. Okay? And you will see that if you have a system which has such a critical orbit, then your system cannot possibly be uniformly partially hyperbolic. Okay? Why is this? Well, if it was uniformly partially hyperbolic, well, then all the stable manifolds should look straight, at least locally, right? And all the center manifolds should look straight. at least 4. But if you have a critical orbit like this, then look what happens, for example, to the center manifold. You have a center manifold, which is this kind of sideways parabola. But if you iterate forward, what will happen is you will contract vertically by an exponential factor, right? So as you iterate forward, you're squeezing, so the center manifold starts to look more and more like. So if you go out far enough, you will see that no matter how local you look, the geometry of the center manifold will always have an arbitrarily large degenerate. So any system with a critical orbit is non-uniformly partially hyperbolic, and we will say, we give this definition, and then I think I'm out of time. So then I'll just state the main theorem, and then I'll conclude for questions. Okay. So we will say that a system definition, say that F is unimodal if the following conditions hold. So first of all, there exists a critical orbit, regular quadratic crit orbit, CM. And the second condition is that, so if you have a regular critical orbit, you have this regular neighborhood, which chases the critical orbit, right? And inside you have this nice uniformization of the local dynamic. So to assume that it's unimodal means that somehow this accounts for all the non-uniformity in the partial hyperbolicity. So we assume that if you take a point which is outside of these neighborhoods, then you have uniform vicinity. So that's unimodal. Unimodal if you take lambda and you take away all of these neighborhoods which cover the critical orbit. So we call these UIs again. So if you take the union of the regular neighborhood of the critical orbits, so let me call this M. Okay. Then this has to be contained in some Pesin regularity. Then we say that it is unimodal. Okay. So this notion of defining a critical point for a diffeomorphism to be a tangency, it's not new. But I think this part of the definition is definitely something that I haven't seen before. This idea that you may have a tangency where it breaks partial hyperbolicity, but that away from this tangency, you have some nice control. Okay. And the main theorem, I'll just state 2 theorems and then I'm done. First theorem is that, well, we talked about how if you have an infinite renormalizable system, you can look at the sequence of renormalizations. So first theorem is that the sequence of renormalization go to a one-dimensional unimodal interval map, 1D unimodal map. If and only if F restricted to the odometer is unimodal. Okay. So that's the first thing. Second thing is, well, it's a weaker theorem. It's actually something that I needed to prove this theorem, but let me state it because I think it'll be more relevant to the theme of this conference, is that if you have a unimodal system like this, which is a non-uniformly partially hyperbolic system, then you can actually find an explicit description of the geometry of the center and stable manifold of every point, not just almost every. So if F unimodal, then, okay, let me be vague, can describe every local stable manifold and every local center. And I think that's rare. I don't know. I think if you have a non-uniformly partial hyperbolic or hyperbolic system, typically you just care about almost every. You don't care about every, but in this case, you can describe every. All right, I'll end here. Thank you.
Okay, time for one question, or if not, yes, please.
Okay. Let me just quickly sketch. So here is the Hénon family. Yeah, so here is the quadratic-like map. And on this quadratic-like map, in the bifurcation locus, you have densely many infinitely renormalizable quadratic polynomials. So what's known for now is that at each of these points, there's a small analytic curve, infinitely renormalizable polynomial, which under renormalization converges to the same 1D loop. Yeah. And what computer simulations has shown is that this actually extends all the way. So the current strategy right now that I'm trying to carry out, is to show that actually they do go up by showing that these maps are unimodal. So here we're using the fact that it converges to 1D unimodal to show that it's unimodal, but if we can find some independent proof of the unimodality of Hénon map, then we will be able to show that renormalization.
Okay, thank you. And other question, we wait for the coffee now, and we thanks again, Jonguk. And we back at 5 and